I will talk about detection of the kinetic Sunyaev-Zel'dovich effect in galaxy clusters. The collaborators are Nabila Aghanim and Salim Zaoubi. First, briefly, what is SC effect? The SC effect is the distortion of the CMB spectrum, which is caused by high-energy electron in galaxy clusters. There are two types of SC effect. One is the thermal SC effect, TSE, which is caused by the thermal motion of gas in galaxy clusters. The other one is kinetic SC effect, KSE, which is caused by the peculiar motion of galaxy clusters. We focus on the KSE, but as shown in the right figure, the KSE is very weak compared to TSE and CMB. The KSE is weak, but there is a motivation to use it. With the KSE, we can study cosmology and astrophysics. This is the formula of the KSE. The deviation of the CMB due to the KSE is proportional to the optical depth and the peculiar velocity along the line of sight. For cosmology, once you measure the KSE, given the optical depths, you can obtain peculiar velocities, which allows to trace the growth of velocities, growth of structures along the cosmic time. But our measurement was not sensitive to cosmological parameters, so in our study, we estimate the peculiar velocity and then trace the distribution of gas in galaxy clusters, which is sensitive to the baryonic effect, such as AGN feedback. To measure the KSE, we use three data sets. One is 30,000 galaxy clusters constructed from the SDSS galaxies in this mass and redshift. Another one is more than 1 million SDSS galaxies from the large-scale structure catalog. The last one is Planck 270 GHz map. We use this map because the TSE is null at this frequency band. To measure the KSE, we use stacking method, but there are several issues. First, KSE is weak. Especially it is 2 orders of magnitude lower than the primary CMB fluctuation. So we use the stacking method to increase the signal to noise, but simple stacking doesn't work because the galaxy cluster can have positive and negative velocity, and the KSE are cancelled out in simple stacking. Also, there are strong foreground-background emissions and the Planck beam. We solve these issues like this. We stack 270 GHz map at the position of galaxy clusters, but before stacking, we filter out large-scale mode larger than 15 arc minutes to suppress the CMB contribution. And also, when we do stacking, we stack galaxy clusters depending on the direction of the radial velocity, which allows to align the positive and negative KSE signal to the same sign, like this. This is also good to suppress the foreground-background emissions. Now, these are cancelled out by the flipping of sign. As a result, we do not find a significant contamination from foreground-background emissions, which is shown later. Planck beam is a limitation. But first, we need to estimate the peculiar velocity of galaxy clusters. For this, we use this linear equation. In our analysis, we fix the cosmology. So these terms are determined from cosmological parameters to estimate the density field around galaxy clusters. we use the SDSS galaxies, assuming the galaxy bias of 2 from other studies. As for the range of integration, we use the distance up to 120 megaparsec, because the early Planck result shows that the correlation of the velocity field reaches up to this scale, 120 megaparsec. And this is the example of the estimated peculiar velocity. A galaxy cluster is located at the center, and the color map is the amplitude of density field from SDSS galaxies. And the blue arrow is the estimated peculiar velocity of the clusters. And as expected, the arrow directs to a high dense region. We also estimate the uncertainty of the radial velocity using the magneticum simulation with mock galaxy and the cluster catalog. First, if there is no redshift space distortion, the linear velocity well correlated with the true velocity with the uncertainty of 180 km per second. But after including the RSD, the correlation is weaker and the uncertainty increased to 260 km per second. The value of the uncertainty is relatively large, and this is not good because the larger the uncertainty, the more the observed KC signal is suppressed in our analysis. But we can use this value of this uncertainty to find out the intrinsic amplitude of the KC signal. And now we have the peculiar velocity of galaxy clusters, and this is a result of stacking. On the top left panel, the solid line is the stacking of all the galaxy clusters using the Planck 270 GHz map. And dot line is the stacking only with negative radial velocities, so galaxy clusters approaching to us. And dash line is the stacking only with positive velocities, galaxy clusters are moving away from us. Because in these three lines, other components such as CMB and foreground emissions are included in average with the same amount, we can extract the KC signal by subtraction, such as dot minus solid and solid minus dash line, which is shown in blue and red line in the bottom. We do the same procedure, but with the additional velocity cut with 100 km per second and 200 km per second in the middle panel and the right panel. As expected, the amplitude of the extracted KC signal increase when we increase the velocity threshold, which is expected only for the KC, which having a correlation with velocity. Next, we compare this result with magneticum simulations. There are lots of nice features on these simulations, and especially for our analysis, the magneticum simulation have the galaxy and cluster catalog, and they also produce the light cone map of the KST. So we can do the same analysis in this simulation as we did with real data. And here is the result of the comparison. The simulation is shown in green lines. As you see, the simulation and data agree pretty well. Here, we restack the galaxy clusters using weight from the radial velocities in order to include all the objects in one profile. which is shown in black line. We also stack the Planck CMB maps with different method, and the result is they are consistent. The point is we get consistent result using the 270 GHz map, including all the foreground background emissions, also using the CMB maps, not including foreground background emissions, which means we do not have significant contamination from the foreground backgrounds in our analysis. We also check our measurement with three different null tests. First one is galaxy clusters are relocated at random position on the sky. And the second one is radial velocity of galaxy clusters are shuffled randomly. And the third one is galaxy clusters are stacked with a noise map at 270 GHz. As you see, all the null tests are consistent with 0, and we did not see any excess in the null test, so our measurement is real. With this null test, we estimate the significance of the KC signal we measured, which is 3.5 sigma. Then we move to the modeling of our measurement. We model the KC signal with a beta model density profile here. For this, we also refer to Praj et al. Measurement with SPT clusters for the core radius and spectral index, and we fit only the amplitude. And we get optical depths of the galaxy clusters, tau of 3 times 10 to the minus 3 for the cluster with a mass of 10 to the 14 solar mass. This result is translated into gas mass fraction, mass of gas over total mass, which is 0.12. Finally, we compare our value of gas fraction with other measurement in X-ray and KC. And this is the X-ray measurement of gas fraction in Gonzalez et al., which shows a depletion of gas in clusters relative to the cosmic baryon fraction. And also in the KC measurement from Sorger et al., they show a lower value than the cosmic baryon fraction. However, KC measurement from Lim et al. Shows the gas fraction is consistent with cosmic baryon fraction down to low mass halos groups. Our measurement is consistent with the cosmic fraction, but also as a measurement shown here. So we need more precise measurement to confirm whether the gas fraction is cosmic fraction or not. In summary, we detect KC signal around the galaxy clusters at 3.5 sigma. The signal was extended beyond the virial radius. The measured KC profile agree with the ones from the magneticum simulations, and the gas mass fraction is consistent with the cosmic baryon fraction, but we need more precise measurement for our better understanding of baryonic effects in galaxy clusters.